least squares estimation of parameters in ODEs. This webinar is an account of some experiments I performed for the least squares estimation of parameters in ODEs. I posed an ODE with undetermined parameters and some noisy data with which to set up a sum of squares of deviations as a measure of performance. Wanted to see if minimizing the sum of squares would provide a reasonable estimate of the parameters. Well, the process was perhaps naive. I started with a guess at the parameter values, solved the ODE numerically, formed the sum of squares of deviations. Then I needed to apply different values for the parameters to see if the measure of performance could be improved. Well, maybe the process wasn't quite so naive. I started with an IVP and I also tried it with a BVP, whose solution I could determine exactly. So I started with exact values of the parameters, generated exact data, added random noise to approximate real-world observations. So then, starting with some approximate values of the parameters, I used Maple's desolve numeric command to generate a solution and use that solution to build a sum of squares of deviations. But I wrote it as a function so that it could be passed to one of Maple's minimization routines. And in the 3 examples that I devised, this process actually worked. So that's what I'd like to share with you in this webinar. How Maple was able to implement what the literature in the past declared to be a difficult problem. Now, just a word about the minimization technique that I implemented in Maple. I made use of this nonlinear program solve command because it takes as an option the Nelder-Mead algorithm. Nelder-Mead algorithm is accessed by stating this option here, method equals nonlinear simplex. Now, nonlinear simplex in the plane is a triangle, and function values are obtained at the vertices of the triangle. You don't need a derivative, you just need function values. Since you're minimizing, you look at the worst value you just computed. Reflect that vertex across the line opposite. Evaluate the function at that new vertex and repeat the minimization. So by means of just function values, you obtain a minimum. Of course, there are safeguards to keep the simplex from distorting and so forth. But this is a method that does not require derivatives because I'm minimizing a function that has a call to Maple's desolve command, and it would be kind of complicated to differentiate that. Now, since we are doing these computations in Maple, we want to set Maple up properly. So initializations, restart, plots package so I can draw some graphs. The optimization package provides the NLP solve command. Linear algebra provides a norm command, and then a nonlinear fit command from statistics. Our first example is a damped nonlinear oscillator with a damping force proportional to the velocity. This is a common ballistics problem. Second derivative, first derivative, this gives you the direction of the square of the magnitude. I started with 2 values for A and B, 2 and 4. Then I picked initial data, a half and 2. So now we generate some observations, some exact observations. Desolve numeric. Now, desolve numeric can return in various ways. So a list of procedures. So when you invoke these procedures, Maple then computes function values. And in this list, the second item is the function that gives you the values of y. And so I grab that, and by just taking the right-hand side of that function, I can rename it to yt. So yt is now a function which in which Maple numerically computes the function values that are the solution of this initial value problem. And now I make a sequence of 51 values. So I'm going 0 to 10, step size 0.2. And it is that sequence that I'm about to add random noise to. The adding of random noise. So we got to generate some random noise. I use normal distribution, mean variance, mean zero variance. I did a little experimenting, 51 sample points. And I added point by point those values to the sequence of exact values that I computed with desolve. Now I use this zip command, which takes a binary operator, here addition, and adds element from the set S, which is the noise, and an element from set Y, which is its sequence exact value. So it pairs up those two values and puts a plus sign between them, and just goes down the list making those additions. This graph is a graph of the solution that I got up here with the noisy data superimposed, so we can see how noisy the data is, how random this random noise is. And it is that random noise that I'm going to try to use to reconstruct the two values of A and B that I started with. Okay, how do you set up, or how do we set up the sum of squares of deviations? And then minimize it. Okay, so first of all, we need this function which sums the squares of deviations. So this is the measure of performance. I call this procedure SS. It takes in two values of the parameters A and B. You got to declare some locals. This pair of statements is a pretty standard pair of statements that you'll find in Maple procedures. It checks to see that these two numbers that the procedure just received are numeric. If they were symbolic, it would choke eventually down below, so you prevent that from happening. Also, I want to stay in the first quadrant for A and B. So if either A or B turn out to be negative, then the return value of this procedure is an enormously large number, and since we're trying to minimize, you haven't deflected or deviated from the minimization process. Here is where Maple's desolve command kicks in. So I'm desolving the differential equation, and you see how I've used DE. Now I'm going to go back here for a second and show you the distinction that I made between DE in large letters and DE in small letters. DE in small letters is the differential equation with the parameters A and B as symbols. DE in large letters is when I replaced A and B with 2 and 4. So down here I'm using small letters, so it's the differential equation with unknown A and B, but the A and B have just been fed into this procedure, and I need to get those values into the DE. So there's your evaluate the DE using the appropriate values of A and B, and this colon dash A colon dash B tells Mabel which of the two A and B to use. And I wanted to use the A and the B that were fed in to the procedure. And then the computation is numeric, and the output is an array of values, because that array of values is going to be converted to a column vector so that I can apply the norm to the difference between those values and the noisy data values. So that's yn means y noisy, and that's a 2 norm, Euclidean norm. And that norm is the return value of this procedure. And it is this that I'm ultimately going to feed in to a minimization routine. Now, I did draw this graph of the surface SS. It's a function of two variables, so I can get a surface out of it. And you can see there is apparently at least one minimum that I'm going to now search for numerically. The minimization step. I use the NLP solve command with nonlinear simplex option. NLP solve, feed it this sum of squares routine. Method is nonlinear simplex. You got to give it some initial point, someplace to start its search. So I'm looking for 2, 4. I tried 4, 1, tried a few things. An evaluation limit so it doesn't run on forever. The return is almost instantaneous. This is the value of the sum of squares. A comes back as 2.2 and B comes back as 4.2, very close to the exact values that I started with. I then took these two values, which is the second member of this list. So this list is what R2 is referring to. And I plugged those numbers into the differential equation and said, let me solve that differential equation with those two numbers and see what that curve looks like. So the red curve in this figure is the exact curve I started with when A was 2 and B was 4. And the green curve is the one that I get when I use these two values, these approximate values of A and B. And the two curves are pretty close. And the dots are the noisy data. So that picture shows that the results are pretty good. And the effort expended is nowhere near as great as it would have been if we were coding this in some primitive language like Fortran or I guess C++ or some language like that, where you did not have access to what are essentially functions. Maple provides those functions in dsolve. It provides those functions in the nonlinear solve command that you do not then have to write yourself. Our second example is also an initial value problem, but it's for a system. It's a nonlinear system of first order differential equations. So it came from Maple Primes. It was posted on Maple Primes. Here is the system. X, Y, Z are the unknowns of the differential equation. A and B are the parameters. They're rate constants. There were 26 values observed for the variable Z. And this is a graph of those data points. And the data itself is hiding behind this table. And here's a statement of how you would see the data. So I've done it with a right click, table, table properties. This dialog comes up, and if you check that box that says show input, then you get to see the data and the commands that drew that graph. I just did a Control Z to revert the step I just took. I think you could go here to Tools, not Tools, a Format. There's a table, and you can get table properties from the Format menu. Okay, so now we need to set up the same sort of SS procedure. And I have rewritten it here. And rather than try to write one fancy piece of code that would accept single ODE, a system, a boundary value problem, initial value problem, it would just becomes a coding issue, and I didn't want to face that. It was easy enough to copy and paste and make the changes that I needed. What changes did I need to do? Here are the three differential equations. You can see here I've labeled the three equations, K1, K2, K3. The initial conditions, the list of variables is different, but I produce an array of 26 values, which I convert to a vector, and I take the norm of the difference between the computed values and C, which is that collection of observed data for Z. I drew this graph of the surface SS, the sum of square surface. It does appear to have at least one minimum, and so I proceed to a numeric minimization. I use again the NLP solve command, give it SS of AB, that's this version of SS, nonlinear simplex. You need some initial starting points for A and B, and a limit to how many computations Maple is going to perform. You can see the sum of squares is very small, and Maple returns a value. A is 0.1 and B is 0.0091. I have graphed the solution for Z using these two values for A and B. I believe that the result is very good. Now, it turns out that you can actually get an exact solution to this system, and in particular, an exact solution to Z of t. Turns out that because of the symmetry in the system of equations, you can add and subtract equations and eliminate things, and you can get this exact solution. All right, so this is the exact solution containing the parameters A and B as parameters, which means you can feed this to a nonlinear fit command. So you are fitting this function to this data. A few options here. The return is the same as you had earlier. A is 0.1, B is 009090. So what did we get here? 00900909. And here you're getting 90909. And if you round this, you'd get a 1 here. So you get an extremely good comparison to the earlier computation. The simplicity with which you can set these computations up in a tool like Maple just makes experiments like this doable. It would be much harder to do this in a programming language like Fortran. Now I just had to try a boundary value problem. I mean, two initial value problems. I just had to try a boundary value problem. So I started over again. I did a restart, brought in the appropriate packages. Just wanted a clean slate. The model I picked was one that I could solve exactly. Second order, linear, constant coefficient, driven. Mixed boundary data, non-homogeneous. I put the parameters in the boundary conditions. Just want to try it. Just want to see if it would work. For a specific problem, I picked 9 and 4 as the A and the B, and I'm going to do the same thing I did earlier. I'm going to solve the problem exactly, generate data, make data noisy, and see if I can reconstruct the 9 and the 4 from the noisy data. So we get an exact solution, and from the exact solution, we get exact observations. This is the exact solution created as a maple function, and these are 21 observations. So it's a boundary value problem. So between 0 and 1, I'm taking step sizes of 1/20th. These are the numbers that I get for y. And just a reminder, you see here, these are blue outputs. Blue outputs, yeah. In other words, a maple computation had to take place for this output to show up. Where is the input that creates these blue outputs? Well, they're hiding behind the table cell. And I showed you how to find those inputs, open the cell, and you can see what computations I set up in order to produce these outputs. Now I need to generate some noise and make the data noisy. So I use the same strategy I used earlier, normally distributed mean 0, experiment here to get standard deviation 0.5. I get a sample size 21. The black dots represent the noisy data. The red curve is the exact solution, and again, the computations that produce this graph and generate the noisy data, they're hiding behind that table cell, and I've shown you how to open table cell to see what took place. Clearly, I'm willing to share this worksheet with anybody who asks, and at the end, I'll tell you how you can contact me for a copy of the work. Now that we have noisy data, we can set up sum of squares of the deviations, and we use the same idea of writing a procedure, SS, whose inputs are the two parameters A and B. Numerically solve the differential equation with the boundary conditions. Output 20 points, or 21 points actually. Make a column vector. Use the norm command to compare those values to the noisy data values. And that norm is the return of this procedure, and it's the measure of efficiency of this process. This is a little sketch of the surface SS as a function of A and B to convince ourselves that there is a minimum that we can hunt for numerically. And finally, the minimization step, in which we again make use of the NLP solve command with the option nonlinear simplex. So there's your NLP solve command. There is the function that we are minimizing. Nonlinear simplex only uses function values. You've got to make an initial guess, and some experimentation goes in there. Return is this list of two items, This is the value of the sum of squares at minimum. And here is a estimate of A and B. Now remember, we started with 9 and 4. This is close to 9. This is close to 4. If I put those two values, which I can grab as the second member of the list that R is, and put those into the differential equation, and I have this boundary value problem, which I can solve numerically. I can draw a graph in green, which is what I would get from here using these computed values of A and B. The red curve makes use of the exact values, 9 and 4. They're pretty close. And the black dots are the noisy data. So I had fun doing these experiments. It was greatly simplified by the tools in Maple. I'm not sure I would have enjoyed having to do this computation with more primitive tools.